One of the last ways we have of describing a distribution, now that we have measures of central tendency, is something called variability. You can imagine a case where you might have the exact same measures of central tendency, the exact same mean, median, and mode for two different distributions, but they still look different. That's because they can have different measures of variability or spread around the mean. Variability intuitively is just how far a score is on average from the mean. And there are two main ways that we have of measuring variability. There's also range, which is just the highest minus the lowest, but for measuring variability, usually people use what are called variance and a standard deviation. And there's just a simple operation to convert between the two, as we'll see in a second. So imagine that I have 5 values. Okay, so I'm going to represent that by x, and my values are going to be 1, 2, 3, 4, and 5. So if we just take the mean of all of these, if we just added up all these different values and divided by the number of observations, in this case there are 5 individual numbers, the mean would be 3. So one way we could do this, if we say that variability is how far the scores are from the mean, is we could take the sum of each of these scores minus the mean. So I'm going to take 1 minus 3, and I'm going to take 2 minus 3. I'm going to add all these together. 3 minus 3, add that to 4 minus 3, and then 5 minus 3. But notice that if I do that, I will get a result of 0 every time. It doesn't matter what my distribution looks like. If I carry out this operation, then that will be a problem. One way that we can get around this is by taking the square of each of these deviations from the mean. And so we can do this by a simple operation. So remember, sum of x, that just adds up all these different values right here. But in R, we can also add in something else, which will be taking the deviation of each score from the mean and squaring that result. So if you enter this syntax right here, remember 3 is my mean, and I square them with this little chevron, then a 2, then this is my variance right here. This relates to our equation where SD squared, which is our notation in the book for variance, is equal to the sum of each value, represented by x, minus the mean, and we square each of those deviations, and then we sum up each of those results. We then divide that by n. Big N, remember, is just the number of observations that we have collected. In this case, we have 5. So I'm just going to assign a variable, just say that n is equal to 5. We can also represent this with some more notation. We can just call this numerator SS, stands for sums of squares, and that's simply the top part of the equation, the sigma x minus m squared. So that's just another way to compress it down. You might see that. Sometimes people will just give you the sums of squares and then expect you to solve for SD squared, assuming you also have big N. So I'm going to go ahead and do this. So remember, this is representing my numerator. This is the sum of squares, taking the deviation of every score squared and summing across all of them. And I simply divide it by n, which in this case is 5. So my variance for this is going to be 2. All right. Not to get too far ahead of ourselves, in this case, we're assuming that this is like calculating the population variance. Like we have every single value that we're interested in. Calculating actual sample variance and standard deviation is slightly different. I just want to give you a heads up because you might see some discrepancy between those calculations. But we will cover that in a couple of weeks. So that is my variance. And to get to standard deviation, it's simply taking the square root of that. So in R, this is square SQRT, and then 2, and this result is going to be my standard deviation. The reason people do that is because it's a little bit easier to interpret and also to work with. Sometimes you can get very, very large variance values, and taking the square root kind of compresses that down. And also it makes more sense because now we're not dealing with square terms, we're dealing with something that's been unsquared. It's removed that operation. And so now we can talk about this number as being how far each score on average is from the mean. One last thing, just conceptually I want you guys to focus on, because this is going to lead into our discussion of z-scores, is if I have a distribution which has a high amount of variability, if I just select one data point or sample at random from that distribution, what is the probability that it's going to be close to the mean or far away from the mean? Conversely, if I have a very tight distribution with a small amount of standard deviation, if I just select one data point at random from that distribution, what is its value likely going to be? Is it likely going to be very close to the mean, or is it likely going to be far away from the mean? So just some things to think about. We'll cover z-scores next time, incorporating some of these concepts into that. But for now, if you have R, feel free to play around with some of those examples that I just worked with. And we'll discuss more of those distributions on the following week.